Let's talk about spanning sets. Okay? Keep in mind a span consists of the set of all linear combinations of a set of vectors from a vector space. And a theorem that we discussed in a different video says that the span is a subspace of the larger vector space V. So we'll look at some examples of some pretty common spans. The first set of examples consists of lines and planes to the origin. Now, we've already talked about how lines and planes to the origin are subspaces. We're going to take a look at vectors that create these subspaces. And a vector that will create the subspace of a line to the origin would be a vector lying along that line with its tail attached to the origin, as you're seeing here. We have a vector V, and the set of all possible linear combinations of V really just boils down to the set of all scalar multiples of V that could be formed. And depending on your values of k, in other words the values of scalars, which will range across the entire set of real numbers, you'll get vectors that are longer than V, maybe shorter, pointing in the opposite direction. And as you collect those different vectors that you create with more and more values of k, you form this line that goes to the origin. And this line that's going to the origin would be the set of all linear combinations generated by our vector V, which is why they're writing this as span and set notation V. So in this case, S, the set S referred to back in that theorem, would simply consist of the vector V. Now in the second diagram, we're in 3 space here, and our set S will consist of 2 vectors, namely V1 and V2, which we have drawn out for us. Here's V1 and here's V2. And as we start mixing different combinations of the vectors V1 and V2, that is, getting expressions of this format, linear combinations of V1 and V2, it traces out a plane that goes to the origin. And it goes to the origin because look at how V1 and V2 are connected. They're connected directly at the origin. Okay? So this plane is basically generated by the vectors V1 and V2. So that would mean that it's spanned by these 2 vectors V1 and V2, which is why you're seeing it written span of V1 and V2. That's what the plane is, or can be relabeled as. To finish this video up, I want to give you sets of vectors that span different vector spaces. We'll start with the n spaces. R2 is spanned by the vectors I and j. In component form, I is 1, 0, and j is 0, 1, which implies that R2 is equal to the span of the set of vectors consisting of just I and j. So basically, these generate all of R2, and later on we'll actually see that these are not the only 2 vectors that generate R2. There will be other pairs of vectors that we can establish generate R2. But for now, we'll just leave it at this. For R3, I, j, and k span it. Here are the component forms of each of those vectors, which implies that R3 is the span of I, j, and k. You can kind of spot a trend right away. Okay, as the dimension increases, the set S where we're getting these generating vectors from increases accordingly. Now, Rn would be spanned by the basis vectors e sub 1 through e sub n, which are basically more generalized versions of I, j, and k. I'll just write it as e sub 1, comma e sub 2, dot, 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 e sub n, which implies that n space is equal to the span of these vectors e sub 1 through e sub n. Now, a set of polynomial vectors can serve as a span of polynomial spaces. P sub 1, keep in mind that P sub 1 would consist of the set of all polynomials of degree 1 or less. And I can give you one version of P sub 1 in set notation. It'd be the set of all polynomials of this format, a sub 0 plus a sub 1x, such that a sub 0 and a sub 1 come from the set of real numbers. And you know, it actually is a different way of expressing scalars of linear combination. You can think of a sub 0 and a sub 1 as scalars of a linear combination involving two polynomials coming from this set. And I'll go ahead and write those out. The first polynomial that you would need to generate this set, we'll call it P sub 0, is the polynomial of the constant polynomial 1. And you would also need polynomials involving the variable x, and the most basic of those, which I'll call P sub 1, is the polynomial x. So in other words, any linear combination of 1 and x would help us to generate polynomials of this format. So P sub 0 and P sub 1 span capital P sub 1. So I'll say P sub 1 is equal to the span of P sub 0 and P sub 1. You would need three polynomial vectors to generate the polynomial space P sub 2, and those vectors are as follows. P sub 0 equals 1, P sub 1 equals x, and we would need a P sub 2, which is going to be x squared, implying that P sub 2 would be the span, that is the set of all linear combinations, of the polynomials P sub 0 through P sub 2. So in general, we are going to need n plus 1 polynomial vectors to generate any given polynomial space. So I'm going to generalize this to P sub n, and vectors that would generate polynomial space P sub n would go as follows. P sub 0 equals 1, P sub 1 equals x, all the way down to P sub n equals x to the n. So P sub n qualifies as the span of those polynomial vectors, P sub 0 through P sub n. I'm going to add a little more detail to these three polynomial spaces. P sub 1 is equal to the span of the polynomials 1 and x. Okay, I think that's a little more telling of what polynomials are being used. P sub 2 is a span of 1x and x squared. And P sub n is the span of the polynomials 1, comma x, comma all the way down to x to the n. And whew, that was a hustle to get through all this. As always, let me know if you have any questions. Otherwise, let's stick in this headspace as we move on to our next video. All right, thank you for watching, and I'll see you soon.